Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory undergraduate combinatorics based on my book, An Invitation to Combinatorics. The subject of this lecture is the relationship between Stirling numbers of the first kind and the second kind, and how do we get one from the other. So here's the motivating question. So bracket n is this set with n elements, 1 through n, and k is a non-negative integer. Stirling numbers of the first kind are the number of partitions of n things into k non-empty circularly ordered subsets. Another way of saying is that is to say how many ways can you seat n people around k non-empty round tables, identical round tables, where the only thing that matters is the relationship between where everyone is sitting with respect to other people and not the actual seat. Stirling numbers of the second kind are the partitions of 1 through n into k non-empty unordered subsets, just putting n things into k piles. How many ways can you do that? And so these sound similar, like one, you just put them in piles. You have n things, you put them in k piles. The other one, you put them in k piles, but you also circularly order those k piles. And but it's not clear how they might be related and why they're called Stirling numbers of the first and second kind. And so we want to know what the relationship is. So outline is that the lecture is that I'm going to tell you what Stirling numbers of the first kind are, what the Stirling numbers of the second kind are, and what's their relation. And how do you prove that? And the way we prove that is actually I'm going to use change of basis matrices from linear algebra. So I'll remind you what that is. And I will also need expansion of falling factors and the Stirling numbers of the first kind, and expansion of x to the n with falling factors and the Stirling numbers of the second kind. Now, I have a whole video, a whole set of videos on linear algebra, including ones on change of bases, although in those I do them from a conceptual linear transformation point of view. But here I'll give you sort of the basics of what you need to know. I also have a couple of videos on Stirling numbers of the first kind, and in fact, one where I prove exactly what I need here for falling factorials. And I have videos on Stirling numbers of the second kind, where we talk about the recurrence relations, give examples and so forth, as well as give something very similar to what I need here, although I will tell you what that exactly is. And then I will give you the proof that Stirling numbers of the first kind and second kind, what the relationship is. So first of all, let's just remind you what these things are. Stirling numbers of the first kind, you have two integers, n and k, both non-negative integers. And the Stirling number of the first kind is denoted by n bracket nk, and is the number of ways that you can seat n people around k identical non-empty circular tables. You have n people walk through the door, you have n tables, they're all the same. You want to seat these people around the tables, and you don't want to leave any table empty, and you want to know how many ways can you do that. The actual seats don't matter. What matters is that if I'm sitting at a table, who's sitting on my right, who's sitting on my left, who's across from me, and so forth. The relations matter. Alternatively, you can say that n brac k, that's how we read that notation, is the number of permutations of 1 through n that can be written as a product of k disjoint cycles. Every permutation can be written as, this is something you learn in basic abstract algebra, and I have videos on that also about cycles and permutations in SN, in symmetric group, and how many permutations of 1 through n, or how many elements of SN are written as product of k disjoint cycles. And by 0 brac 0 is 1. You can either define it that way or properly interpret what Stirling numbers of the first kind are. And they have a recurrence relation. Again, watch the video that I have for that this n brac k is n minus 1 brac k minus 1 plus n minus 1 times n minus 1 brac k. If you want to find that yourself, just do a thought experiment. Think about seating people around a k non-empty table, and have one of your friends come late, and see what you can do with them and where they can sit to find that. From that, you can find the table values, and we can generate as much of this as we want, but that doesn't really help us in terms of understanding exactly what the relationship is with the Stirling numbers of the second kind. And what are those? Stirling numbers of the second kind are denoted by n brace k, or n subset k, and actually I seem to also call it n squig k, nobody else does. read n subset k or n brace k, is the number of partitions of a set with n elements, and our set with n elements is 1 through n, but it could be any set with n elements, into k non-empty parts. Basically, you have n things and you want to put them in k piles. How many different ways you can do? Or you have n of your friends and you want to put them in k teams. How many ways can you do that? Or you can think of this as putting n distinct balls into k identical boxes, but at least one ball per box. And they also have a recurrence relation. And you also find that by thinking of what to do with the last thing that you want to place in a pile. And brace k is n minus 1 brace k minus 1 plus k times n minus 1 brace k. Watch my video on Stirling numbers of the second kind to see a proof of that if you can't think of it on your own. But the best thing to do is stop the video and try to come up with that recurrence relation yourself. You can do it. Using that recurrence relation, you can find a table of values for these Stirling numbers of the second kind, and you can go as far as you want with them. Okay, now how are they related? If you pick a specific n and k and ask how are these two numbers related, how many ways can I put n things into k piles, or put n thing into k piles and then put each pile into a circle or permutation, it's really hard to say what that relationship is. So, for example, here's the table of Stirling numbers of the second kind. Here's the table of or matrix of Stirling numbers of the first kind. And if you look at these numbers, there's some of them that are related to some of the other ones, but it's hard to come up with a relationship. However, the matrices are actually related. So each one of these is a 6x6 matrix that has all the Stirling numbers up to n equals 5 and k equals 5, and the matrices are related. How are they related? Well, first, you have to, instead of the Stirling numbers of the first kind, you have to look at the signed ones. And so what are those? Those are, you multiply each one of the n brat k's with minus 1 times n plus k. So some minuses come true. Then you have these two matrices, and the two matrices are inverses of each other. They're matrix inverses. If you multiply the matrices, you get the identity matrix. Now, that's an amazing relationship, because it says that if you sort of know a whole bunch of Stirling numbers of the first kind or second kind, you can find a whole bunch of the other ones. But you can't sort of find one by one, this one from that one. But if you know a whole lot of them, you can find those other ones. Okay, so now how are we going to ever prove that these two matrices are inverses of each other? So Sn is going to be the matrix of Stirling numbers of the second kinds, and little Sn is going to be the matrix of signed Stirling numbers of the first kind. And we want to prove that these are inverses of each other. And you can do that by showing that their product is the identity matrix entry by entry. And you can actually do that. But you would actually need the same ingredients that I will prove to do it my way to do that. And if you do that, then you don't have to think about linear algebra. But then it becomes sort of tedious and sort of uninspiring. So what I will do is that actually I will bring in linear algebra. Well, it's about matrices, so that's not so surprising. So I will look at the vector space of polynomials of degree less than or equal to n. That's a vector space, and it's an n plus 1 dimensional vector space. If you don't know what I'm talking about, go watch my videos on linear algebra. You should know linear algebra, and I have a full course of linear algebra videos that you should be watching. And this vector space has a basis, and because it's n plus 1 dimensional, the basis will have n plus 1 elements in it. 1x squared to x to the n is a basis. All that means is that these are linearly independent. You can't get any one of them. All of them are necessary. You can't get any one of them from any of the other ones. And every polynomial of degree less than or equal to n is a linear combination of these. But this is not the only basis. You can also write falling factorials. So I will remind you what those are in a second. But those are, you start with x and multiply by x minus 1, x minus 2, x minus 3, and so forth. And that will be a different basis for the same vector space. And when you have that, you can find, to go from one basis to another, we have these things called change of bases matrices. So, and what we will prove is that the change of basis matrix from that first basis, that standard basis, to B2 is going to be the transpose of the matrix of Stirling numbers of the second kind. And the change of basis matrix from the falling factorials to the powers to the standard basis is going to be the transpose of the signed Stirling numbers of the first kind. And if you have two change of basis matrices from one basis to one, and then from the other back to the first one, again, linear algebra tells us that these are inverses of each other. So and transpose capital S and transpose, and little s and transpose are inverses of each other. But then if you take transpose of that, then that means that the Stirling numbers, the matrix of Stirling numbers are inverses of each other also, and we will be done. Okay, so that's quite an interesting story. So to start, let's remind you what the change of basis matrices are. And now, even though I'm interested in polynomials, I will remind you in terms of R3, because that might be more familiar. So R3 is a vector space. You can add, you can multiply it by scalars. That's what a vector space is, where you can have the games of addition and scalar multiplication, and they follow nice rules. And R3, the three-dimensional space that we live in, is certainly such a vector space. And it has one basis is the standard basis, what you might know as IJK, or 100010001. That's a basis. They're linearly independent, and you can get every element of R3 as a linear combination of them. But here's another basis for it. Not so nice, but there's another basis that I call V1, V2, and V3, -1, 2, 0, 2, -3, 2, and -1, 1, -1. That is also a basis for R3. There's three elements, and for example, you can check that they're linearly independent, and if you have the right number of elements and they're linearly independent by something I like to call 2 out of 3 theorem, watch my video about that, it'll automatically will span, and it's a basis. Okay. So these are both bases for R3. Now, a vector walks through the door, and this vector, we're giving its coordinates, the coordinate vector of this, not the usual coordinates of that point in R3. V is an element of R3, but we're not given the usual. By usual, I mean the coordinates of it in terms of S, the standard basis. If someone says here the point 135 in R3, they mean you need one of these, 3 of those, and 5 of those. They're giving you the coordinates with respect to the standard basis. But this point, they've given me the coordinates with respect to this weird basis B. So -5, -3, 2 are not really what you think of the coordinates of that point, but are the coordinates of that point, but with respect to this basis from the point of view of the basis B. So we're measuring everything, we're scaling everything in terms of B. So what that means is that, so when you say you have the 0.352 in terms of the standard basis, that means that scale this guy 3 times, scale that time 5, this one 2, and then add them. And by the way, those are why 3, 5, and 2 are called scalars. And because they're scaling these guys, and then you add them and you get the 0.352. That's giving you the coordinate, the 352, then it's the coordinates of that point with respect to the standard basis. Now, -5, -3, 2 is also coordinates, but in terms of B. And what I want to know is that, okay, if that's the case, then what is the coordinates of V with respect to S? And the answer is that that's, well, not that hard to say that the coordinates of this point with respect to B is -5, -3, 2. It means that you scale V1, V2, and V3, which are the basis elements in B, by -5, -3, and 2, and then add them, just like what you would do in otherwise. So V is -5 V1, -3 V2, plus 2 V3. Now, you can take that and write it as a matrix multiplication thing. Whenever this is a matrix where its columns are V1, V2, and V3. So you took those V1, V2, and 3 and put them in columns and multiplied that by this -5, -3, 2. Why is this the same as that original thing that I said, that linear combination? Because when you multiply a matrix by a column vector, you always get a linear combination of the columns of the matrix where the scale is coming from the column vector. I have a whole video on that. So watch that if you're wondering what am I talking about. So if you have this matrix where the columns are V1, V2, and V3 and multiplied by this column vector -5, -3, 2, you get exactly -5 V1, -3 V2, plus 2 V3, which is what V is. Now, V1, V2, V3, these things that I wrote here, I wrote them as if I sort of knew what they are. But what those things are really the coordinates of these points with respect to the standard basis. So what do I mean by V1 is -1, 2, 0? I mean it's -1 of these, but 2 of those, and 0 of those. And so therefore, instead of writing V1, V2, and V3, I can say, well, these are the coordinates of V1 with respect to S, the coordinates of V2 with respect to S, and the coordinates of V3 with respect to S. And that's what I multiplied by -5, -3, 2 to get actually V. And what I mean by V, I got the coordinates of V with respect to the standard basis. So at the end of the day, this is what I'm getting. I found myself a matrix that when I multiply by the coordinates of V with respect to B, it gives me the coordinates of V with respect to S. What is that matrix? That matrix, its columns are the coordinates of the new basis, the B basis, V1, V2, and V3, in terms of the standard basis. So you take your new basis, you write them in terms of the old basis, and make a matrix out of it. And then that matrix always no matter what vector you give it, if you give the coordinates with respect to the new basis, we'll give, by multiplying, you get the coordinates of that vector with respect to the standard basis. And this is what a change of basis matrix is. A change of basis matrix changes coordinates from one basis to another. And this is how it's found, and this is what it does. Now, this is was somewhat straightforward. Although if you don't know what I'm talking about, you're completely lost. You need to go learn some linear algebra. But if you're not lost, this sort of made sense because I used one of these as standard basis. But the same argument works with a little bit more detail for any base, if these were any two bases. But again, if you're reluctant to believe that, watch my videos on linear algebra where I go into much more detail. But so let me repeat myself of what I said and sort of write it more formally. So I have a vector space V, but I think I have sort of two copies of this vector space. And I have two bases for them, really, a basis B and a basis S. And I want to find this matrix P, which is a change of basis matrix, sometimes called the transition matrix, from the basis B to the basis S. Okay, so what's the deal? What does this matrix wants to do? This matrix wants to translate from the basis B. If you have the coordinates of a vector with respect to B, this matrix P translates it to the coordinates of V with respect to S. So B and S are bases for this n-dimensional vector space V. This P, the change of basis matrix from B to S. Here are some facts about it. First of all, as I just explained, what it is that I can tell you what its columns are. And each of its columns are, you take the elements of your basis B, you want to go from B to S, so you take the elements of the basis B and write them in terms of the basis S. There's no free lunch. Yeah, you can't just come up with a matrix without doing some work. And the work you're going to do, because you want to go from B to S, is go from B to S for these vectors V1 through Vn, which are the basis for B. You do that, and then you get this matrix, and the matrix then will do it for all the other vectors. So if you have any other vector V in B, and if you give the coordinates V with respect to B, and you want the coordinates V with respect to X, all you have to do is multiply the matrix P, this matrix that we just made, by that. So the first property tells us what the matrix is. The second property does what the matrix does. But we can also go the other way. So sometimes you might not like going from B to S. You want to come back. You were happy in B, somehow made your way to S, and now you want to come back. And for that, you need the change of basis matrix from S to B. But that's going to be the same thing. You take the elements of S and write them as in terms of B. So you write the coordinates of every element of S in terms of B, make those column vectors, and make a matrix. So that's what it is. But what this matrix also is P inverse. And now that part is not that hard to see because these vectors are come from bases, they're going to be linearly independent. So this matrix is going to have rank n, and therefore it's going to be invertible. And if you have P times VB equals VS, you can multiply by P inverse on the left, and you get the coordinates of V with respect to B is the coordinate inverse with times V with respect to S. And that tells that P inverse also does this job. And the reason that this is actually equal to P inverse for sure is because there's only one matrix that can do that, and that's not too hard to show. Again, watch my videos on linear algebra for more detail. But the three things we need to know from change of basis matrices is first how you find them, and then what does it do when you multiply P, that matrix, by the coordinates with respect to B, you get the coordinates with respect to S of any vector. And also, if you have a change of basis matrix from one basis to another, and then you have the change of basis matrix from the second basis to the first, those two matrices are inverses of each other. Okay, so, but what we want is change of basis for polynomials. And so let's talk about what we want to show. So again, Sn, capital Sn is going to be matrix of Stirling numbers of second kind. Little sn is going to be the matrix of signed Stirling numbers of the first kind. And I'm going to look at the vector space of polynomials of degree less than or equal to n. And this is an n plus one dimensional space. And one reason for that is that this is a basis for it. In fact, this is what is called the standard basis for polynomials of degree less than or equal to n. 1x, x squared through x to the n. These are linearly independent, and they span this vector space. Their linear combinations give you exactly every element of this space. Another second basis is the falling factorials. And what are those? The falling factorials, the 0th one is just polynomial 1, and the other ones you start with x and just multiply by x minus 1, x minus 2, and so on. It's sort of like a factorial, but a truncated factorial. You stop after k terms. X minus 1, x minus 2. The reason the last one is not x minus k, but it's x minus k minus 1. So we end with k minus 1 because we started with 0 and we want k terms. Okay, so that's also second basis. None of them is a linear combination of the ones before. They're linearly independent. They're the right number of elements, so it's a basis for the vector space. And what we want to show is that the change of basis matrix from B2 to B1 is the signed Stirling numbers of the first kind, actually the transpose of that. And the change of basis matrix from B1 to B2 is the transpose of the matrix of Stirling numbers of the second kind. And then that will tell you that these transposes are inverses of each other. But if the transposes are inverses of each other, then so will the actual matrices, and we will be done. And how do we know that transposes are inverses of each other? Because change of basis matrices from one basis to another, and then from that one back, are always inverses of each other. So our job is to be able to find these change of basis matrices, is we have to write the following factorials in terms of powers of x, and we have to write powers of x in terms of following factorials. And these I have done at various stages in previous videos, but I will remind you. So first, about the following factorials. Now, in terms of powers. So the following factorial function is defined, as I said, x times x minus 1 times x minus 2 all the way till x minus k plus 1, and the 0th one is defined to be 1. And if you multiply these out, you will see that the coefficients are the signed Stirling numbers of the first kind. That's actually surprising and not clear at all why that is. It needs a proof that that's the case. So let me just say that as a theorem. So SNK is going to be the signed Stirling numbers of the first kind. And again, Stirling numbers of the first kind are what? Is the number of ways that you can seat n people around k non-empty tables. Okay, k round non-empty tables. And the theorem is that if n is a non-negative integer, then when we expand these following factorials, you will get the coefficient are going to be these signed Stirling numbers of the first kind. And this theorem, I'm not going to prove to you here because I have actually a whole video just devoted to the proof of this. And you should watch that if you want the proof, and if you don't believe the pattern, which you shouldn't really. You should really watch the video to see what the proof is, or try to come up with it yourself. That's even better. So it's a little bit hard to do that, but you might be able to succeed. So lil Sn is the matrix of signed Stirling numbers of the first kind, and then what is that? Is that it's an n plus 1 times n plus 1 matrix, and its entries are these signed Stirling numbers. The ij entry is minus 1 to the I plus j times I brac j. And so if that's the case, if you believe that theorem, and again, subject of a previous video, then that means that I wrote xn, the following factorials, in terms of powers of n. And so these coefficients are going to be a column, and that's why I'm getting a transpose, because one row of these signed Stirling numbers is going to become a column of my change of basis matrix. So if I take this basis and the standard basis for polynomials and the following factorial basis for the polynomials, then the transpose of the matrix of signed Stirling numbers of the first kind will be the change of basis matrix, because when you write the following factorials in terms of those, you get a row of this matrix, and then what you have to do is make that into a column, and therefore you're going to get the transpose. So again, this is all done. It's all based on this one theorem that I'm not giving you the proof in this video, but I gave it in the previous video, and I remember that because actually I just taped that. So for the other direction, I will actually say something about the proof. In fact, I'll give you the complete proof. So now in here, we need to write xn in terms of following factorials. So if I do that, this is sort of harder to actually do. It's not just multiplying out. You will see that the coefficients are the Stirling of the Stirling numbers of the second kind, and there's no negatives either. So if you take powers and write them, then you do get Stirling numbers of the second kind walking in there and showing their face. Surprising. And so that actually does need a proof. So n brace k, or n subset k, that's the number of ways of putting n things into k non-empty piles, Stirling number of the second kind. And the theorem that we want to prove is that if you take x to the n, x is an indeterminate, is unknown, x to the n, you can expand it in terms of falling factorials using Stirling numbers of the second kind. Again, somewhat surprising. And then from that, we will say that, okay, well, let's make a matrix out of these Stirling numbers of the second kind. Again, an n plus 1 times n plus 1 matrix, n plus 1 rows, n plus 1 columns, where the ij entry is one of these guys. And again, this means that we found the change of basis matrix, this time from B1 to B2, because to find the change of basis matrix from B1 to B2, you have to take one of these and write one of the powers and write them in terms of the falling factorial. And this theorem tells us that. It tells us that you get a row of Stirling numbers of the second kind. That row then becomes a column of your change of basis matrix, which is why you get the same matrix as the matrix of Stirling numbers of the second kind, but sitting on its side. In other words, you get the transpose. So, and if you do this, so if you know this theorem, then we're done. Then we have these two change of basis matrices, they're inverses of each other, and we have proved the remarkable relation between Stirling numbers of the first kind and the second kind. But why is this theorem true? Now, some of it I've actually proved in a previous video, but I will tell you. So here's what I want to prove, that if I take x to the n, I can write it in terms of falling factorials using Stirling numbers of the second kind. And here's the proof strategy. The proof strategy is actually sort of interesting. I'm going to define a function, a polynomial, f of x, which is going to be x to the n. So I'm going to x to the n minus that whole mess that I want to show x to the n is equal to. So what's my hope? What am I wishing? I'm wishing that f of x to be the zero polynomial. That's what I want to show. But a priori, before proving that, all I know is that it's some polynomial, and it looks like it's of degree less than or equal to n. It's actually probably degree less than that, but some polynomial of degree less than or equal to n. And what I want to show is that the zero polynomial. How am I going to do that? Well, I will pull out a fact from abstract algebra, which you need to watch my abstract algebra videos if you want a proof of it, although you believe this one. This is something that we have intuition for and sort of makes sense. That a non-zero polynomial of degree n has at most n roots. Roots are things that you plug in the polynomial and you get zero. So if a polynomial is non-zero, it can't have more than its degree. The number of roots can't be more than its degree. And in this case, we'll show that if you have any positive integer t that's greater than n, and there's plenty of those, whatever n is, there's plenty of integers greater than it, all of those, if you plug it into f, you get zero. So f will have infinite number of roots, and therefore it has to be the zero polynomial, and therefore these two sides have to be equal, and therefore we're done. So all we have to do is show that if I plug in an integer t greater than n instead of x, then I get zero. So I actually need to, in other words, I have to prove this identity for positive integers, and that's actually a technique in combinatorics, or not in combinatorics, in when we want to deal with sort of generating function kinds of things like this, is to say that, okay, define a polynomial and try to show that it has too many roots. Okay, so the thing that I want to prove again is that powers of x can be written as falling factorials using Stirling numbers of the second kind. And the thing that I reduced it to, that was the previous slide, was that if you pick an integer greater than n, then the identity works. If the identity works for integers greater than n, then it will work for everything, again, because of that polynomial argument. Okay, now why is this? For this, we do a thought experiment. We say that we have n distinct balls, and we want to put them in t distinct boxes. This was actually the subject of a video. I have a video on formulas for Stirling numbers of the second kind, which you should watch. Pretty interesting video. And in that, I go into this in actually a lot more detail than here, although more detail probably isn't necessary. So number of ways of placing. So you have n distinct balls, t distinct boxes. You want to know how many ways can you put the balls in the boxes. Well, the first ball, how many choices you have? You have t choices. The second ball, how many choices you have? You have t choices. Third ball, t choices. And there was n balls, so the total number of choices is t to the n. The multiplication principle, pretty easy. But you can think of this differently. You can say, well, what if the original way, you could have put everything in the same box, for example, or put them all in different boxes, or some of them, so on. But now we will be a little bit more precise in the way we're going to put the balls in the boxes. We're going to say, well, maybe I'm going to put them in n distinct boxes. I mean, I have n balls. Maybe I'll put them in all different boxes. So to do that, I'm going to separate them out into little piles of one. Well, there's only one way to do that. Just separate them out. And then I'll say, how many choices do I have for this guy? Well, I have t choices. Well, how many choices do I have for the second one? Well, I don't want to put it in the box that I just put the other one, so I have t minus 1 choices. Then the next one, t minus 2 choices, and so forth. So I get a following factorial. I get t starting with t, and I get n factors. So that's the following factorial t going down n factors. So that's how many ways I can place the n distinct balls in t distinct boxes. If if I'm using n different boxes, non-empty boxes. But maybe but the original problem didn't have that restriction, but maybe I'm putting in n-1 boxes. If I want to put them in n-1 boxes, then I first put them in the n balls into n-1 piles, and the number of ways I can do that is n brace n-1, and then I will put the piles in the boxes. For the first pile, I have t choices, then t minus 1 choices, but this time I have n minus 1 piles, so the following factorial is going to be t going down n minus 1 factors. And then I'll do the same thing with, what about if I want to put them in n minus 2 non-empty boxes, and everyone else is going to be empty. So I'm going to put them in n minus 2 piles. The number of ways I can do that is n brace n minus 2. And then for the first pile, I have t choices, second pile, t minus 1 choices. And so I get another following factorial. And this continues all the way till the end. And I've now proved what I wanted to prove, is that t to the n is the same as this through this thought experiment. So a recap. So what did we prove? That if you take the matrix of Stirling numbers of the second kind and the signed Stirling numbers of the first kind, that these two matrices are inverses of each other. And our main ingredients were actually two things. One was to write powers of x in terms of following factorial, and one to write following factorials in terms of powers of x. And in fact, using these two, as long as you know these two, you don't have to go through the whole change of basis matrix, although I really like that because that gives you sort of a conceptual view of why matrices are inverses of each other. You could just use this and try to see why entry by entry, the product of these two matrices is identity. This was the sixth video in a series of that I have so far of videos on Stirling number kind. And like my videos and subscribe to my channel if you like to be subjected to videos like this on your feed, and keep hydrated at all times. See you next time.